Okay, let's unpack this. Imagine a single book, right? Leather-bound, printed way back in 1687, in Latin no less. And this book, it didn't just explain the universe, it fundamentally changed how we think about it. It kind of smashed this old idea that Earth and the heavens were totally separate things, unified them, one grand, elegant system, all mathematically precise. So today, yeah, we're doing a deep dive into that exact book, Isaac Newton's Philosophiae Naturalis, Principia Mathematica. We just call it the Principia. Our mission here is really to pull out the core genius, understand the ideas, the context, the incredible legacy. We want you to walk away really getting why this was such a pivotal moment, a total game changer. And we're using a fantastic essay as our guide, Newton's Principia Mathematica, a scientific revolution. It lays out the background, the content, the impact really clearly. Get ready, because we're going to connect some amazing dots here.
It's fascinating, isn't it? Because Newton wasn't just working in a vacuum. He was, as the saying goes, standing on the shoulders of giants. The 17th century, I mean, it was just buzzing with intellectual energy. The scientific revolution was in full swing. Think about who came before. You had Nicholas Copernicus, right, back in 1543, challenging that whole Earth at the center idea. Huge.
Right.
Proposing the sun was actually at the center of the heliocentric model. Then Galilei comes along, uses his telescope, finds real evidence for it, like seeing Jupiter's moons go around it, not Earth. And Johannes Kepler, he meticulously worked out the math for how planets move, those elliptical orbits. Plus, you had philosophers like René Descartes thinking about the universe as a kind of machine, mechanical explanations.
Okay, so you've got all these incredible pieces floating around, a new map of the solar system, Kepler's math describing the paths, this mechanical view, but it still feels like something's missing, right? Even with geniuses like Galileo and Kepler, what was the big gap?
Exactly. That's the key. They had brilliant descriptions of what was happening. Kepler could tell you how a planet moved, but nobody had a single unified theory for why. Why ellipses? Why do things fall down on Earth? Were these, totally separate rules for Earth and the heavens? Or was there some deeper connection? That was the puzzle. And this brings up a really interesting point. What actually pushed Newton to write this colossal work? To tackle that why? It actually started with a very specific question from a friend, Edmund Halley.
Halley, like the comet.
The very same. Halley visited Newton and asked him, basically, if the sun pulls on planets with a force that drops off with a square the distance, an inverse square law, what path would a planet take?
Ah, like how light gets dimmer the further away you are.
Precisely.
Yeah.
And Newton, it turned out, had already done a lot of thinking about this.
Yeah.
He actually had proof showing it would be an ellipse. Halley was just blown away and basically urged him, maybe even pestered him a bit, to publish it all, to expand it into what became the Principia.
Wow, what a great origin story. So Halley's question was the spark. And Newton didn't just scribble down the answer. He built this enormous structured argument. How did he even organize it? Was it just one big block of text?
Oh, no, far from it. It's incredibly structured, almost like an architectural blueprint. The Principia is divided into 3 distinct books. Each one carefully builds on the last. It's a very logical progression.
3 books. Okay. So what's in book 1, The Motion of Bodies? Where does he start?
Book I lays the foundation, sets the stage, you could say. He starts with clear definitions, what is mass, what is force, and then, crucially, he introduces his 3 famous laws of motion. He uses these really rigorous geometric proofs to show how bodies move under different forces, especially central forces like gravity. It's the mathematical engine for the whole work.
Okay, laws of motion established. Did he then just leap straight to the planets and stars?
Not quite yet. Book 2 is interesting. It's called The Motion of Bodies in Resisting Mediums. Here, he dives into the real-world complexities, like how objects move through air or water, dealing with resistance, drag.
Ah, so fluid dynamics.
Exactly. It anticipates a lot of later work in fluid dynamics, things like viscosity, drag forces. It might seem less glamorous than, say, planetary orbits, but it's super important for understanding motion in the real world. Think about designing ships, or even just how rain falls. Newton was tackling that too.
That makes sense. Grounding the theory before launching it into space, basically. Which brings us then to book 3, The System of the World. This must be the big payoff, right?
Absolutely. Book 3 is the grand synthesis. This is where he takes the laws and the math from books 1 and 2 and applies them to the entire cosmos. And here's the killer part. He shows the exact same laws, explain why an apple falls from a tree, and how the moon orbits the Earth. Yeah. This is where he fully unveils the law of universal gravitation. It connects everything. He uses it to explain the tides, planetary orbits, comets, even tiny variations in Earth's rotation over centuries, the precession of the equinoxes. It all fits into this one framework.
That unification idea is just staggering. But let's back up slightly to Book I and those three laws of motion. They're so fundamental, aren't they? Bedrock of classical mechanics.
Totally. They fundamentally shifted how we understand motion itself. Take the first law, the law of inertia. It says, everybody continues in its state of rest or uniform motion in a straight line unless compelled to change that state by an external force.
Sounds simple, but that was a huge break from the past, wasn't it? People thought things naturally just stopped moving.
Exactly. It directly challenged Aristotle's view, held for millennia, that rest was the natural state.
Hmm.
Aristotle thought you had to keep pushing something to keep it moving. Newton, building on Galileo, said, nope, motion is just as natural as rest. An object will keep doing what it's doing, resting or moving steadily, unless a force messes with it. A massive conceptual shift.
Okay, then the second law. The change of motion, or momentum, is proportional to the applied force and takes place in the direction of the force.
This is where the math comes in strongly, right?
Right. This gives us the quantitative punch. It leads directly to that famous equation, 5-nth motion. Force equals mass times acceleration. Suddenly, you could calculate precisely how much a force would change an object's motion. It made mechanics predictive and mathematical.
And the third law. For every action, there is an equal and opposite reaction. This one feels really intuitive.
It does feel intuitive, but it's profound. It emphasizes that forces always come in pairs. Interactions. You push on a wall, the wall pushes back on you. A rocket pushes gas down.
And gas pushes the rocket up.
Exactly. Rocket science relies completely on this law. It underpins basically every interaction in the universe.
Okay, so we have these powerful laws. Now, connecting back to Book 3 and that grand unification, you said the law of universal gravitation was the game changer. Tell us more about that. It really was the linchpin. Universal gravitation. Newton proposed that every speck of mass in the universe attracts every other speck of mass. And the force of attraction depends on how massive they are, more mass, more pull, and how far apart they are. Specifically, it's proportional to the product of their masses and inversely proportional to the square of the distance between them. You might have seen the formula. 1 Dalek equals G frac M1 milli 2.
That inverse square thing again.
Yes. It means gravity gets weaker really fast as things get further apart.
And the revolutionary part was applying this everywhere, not just on Earth, but out in space, too.
Precisely. For centuries, people thought earthly physics and heavenly physics were different. Earth was corruptible, changeable, the heavens were perfect, eternal, different rules applied. Newton just demolished that wall. He showed the same force pulling the apple down as what keeps the moon orbiting the Earth and the Earth orbiting the sun.
So the cosmos wasn't some mystical separate place anymore?
It was just a bigger, governed by the same physical laws we experience right here. One unified system. That was the universal part of universal gravitation, and he proved it mathematically. He showed how Kepler's laws, those descriptions of how planets move in ellipses, could be derived directly from his law of gravity. So he didn't just describe how, like Kepler did.
No.
He explained why. He provided the underlying physical mechanism. It was a stunning piece of deductive reasoning.
It's just amazing. And the way he presented it with such mathematical rigor, you mentioned he used geometry mostly, even though he'd invented calculus.
Yeah, that's fascinating, isn't it? He used the geometric style familiar to mathematicians since ancient Greece, likely to make his arguments more accessible and less controversial than using his brand new fluxions, as he called calculus. But underlying it all was this incredibly rigorous approach. He wasn't just dreaming up theories. He famously stated, hypotheses non fingo. I frame no hypotheses, meaning his laws weren't just guesses. He deduced them from observed phenomena, from the actual behavior of things.
So this focus on observation, evidence, mathematical proof, what did that do for science going forward?
It set a new gold standard. It cemented the idea that science progresses through careful observation, measurement, and testing theories against reality using the language of mathematics. It really solidified the scientific method as we know it. Empirical evidence and mathematical demonstration became paramount.
Okay, so obviously a revolution in physics, but you get the sense the ripples went much, much further than just science labs. How did the Principia change broader thinking, philosophy, maybe even religion?
Oh, absolutely. The impact was immense. First, just the unification of knowledge was huge, showing the same rules applied everywhere. Earth, sky, tides, planets broke down old barriers in thought. And his method, that rigorous mathematical approach, profoundly influenced the scientific method itself. Scientists like Laplace, Lagrange, Euler, they built directly on Newton's foundation, using math to unlock Moore's secrets of the universe.
And what about beyond science? Its effect on the Enlightenment seems really key.
Definitely. Thinkers of the Enlightenment, people like Voltaire, Kant, John Locke, were incredibly inspired. They saw Newton's success in finding rational, understandable laws for the physical universe and thought, hey, maybe we can do the same for human society, for government, for morality. It fostered this powerful belief in reason, order, and the idea that the world, and even human affairs, were fundamentally discoverable and maybe even improvable through rational inquiry. And even religion felt the impact. Newton himself was devoutly religious and saw his work as revealing God's magnificent design and order in the cosmos. His discoveries were widely used in natural theology arguments for God based on the intricate workings of nature, though, of course, how people interpreted the religious implications changed over time.
It sounds almost too good to be true. You'd think everyone would just immediately say, wow, Newton nailed it. But even revolutionary ideas get pushed back, right? Were there criticisms?
Oh, for sure. It wasn't universal praise immediately. A really big sticking point for some was that concept of action at a distance.
Gravity working across empty space with nothing touching.
Exactly. Philosophers like Leibniz, who was also developing calculus independently, found that deeply troubling. How could gravity just reach across the void? To them, it smacked of the old occult qualities, like mystical forces that the new mechanical philosophy was supposed to get rid of. They wanted a mechanism, something pushing or pulling directly.
That's a fair philosophical point, actually. So, was there a competing theory that offered a mechanism, or did Newton's theory just work so well people eventually accepted it, mystery and all?
There were attempts at mechanical explanations, like vortices or flows of invisible particles, but none of them could actually predict planetary motions with anything close to the accuracy of Newton's law. Ultimately, the sheer predictive power of Newtonian mechanics won the day. It just worked. It explained existing observations, it predicted new phenomena like the slight bulge at Earth's equator or the precise return of Halley's comet, which Halley himself predicted using Newton's methods.
Ah, so Halley got his comet named after him, partly thanks to Newton's math.
In a way, yes. That predictive success was just undeniable. It became the framework everyone had to work within.
So looking back now, centuries later, the legacy is just immense. It's woven into everything. What are the biggest takeaways for its lasting impact?
Well, first and foremost, it's the absolute foundation of classical mechanics. Physics, as a predictive science, really starts here in many ways. It reigned supreme until the early 20th century, with Einstein and quantum mechanics looking at the very fast, the very massive, and the very small.
And for astronomy and space science, it's just indispensable, isn't it?
Completely. Predicting orbits, understanding planetary interactions, it led directly to discovering Neptune based on wobbles in Uranus's orbit predicted by Newtonian gravity. And today, every rocket launch, every satellite orbit, every probe sent to Mars or Jupiter relies fundamentally on Newton's laws. They are the roadmap for navigating the solar system. And don't forget engineering and technology right here on Earth. Building bridges, designing cars, understanding how machines work. So much of modern engineering still rests squarely on Newtonian principles. Engineers use these laws every single day.
And it's important to remember, even with Einstein's relativity, which is crucial for things like GPS accuracy or understanding black holes, the internals laws aren't wrong. They're an incredibly accurate approximation under most conditions we experience. Relativity is more like an extension or refinement for extreme situations.
Right.
So pulling it all together, Isaac Newton's Principia Mathematica, it wasn't just a book, it was like a key unlocking a whole new way of seeing reality. Laws of motion, universal gravitation. He gave us this complete mathematical toolkit to understand everything from apples falling to planets orbiting. Just incredible.
Absolutely. Unified science, it sparked the Enlightenment. It set the standard for scientific inquiry for centuries. It really stands as this towering monument to what human reason can achieve. Observation, math, deduction, all coming together to reveal nature's underlying order. Reflecting on the Principia really highlights this amazing human ability to find unity in apparent diversity, to connect the dots. And it makes you wonder, doesn't it? What seemingly disconnected phenomena are we observing today? Think about mysteries like dark matter, dark energy, the weirdness of quantum gravity. Are we just waiting for another Newton-level insight, a new framework to tie it all together to some elegant, maybe complete unexpected, unified theory? That's the ongoing quest.